I'm Brittany Brown and I work in ES62, the Environmental Control and Life Support Design and Development branch.
And I am Enrique Jackson. I work in Materials and Processing Laboratory, EM22 in the chemistry team.
We are partnering together on a can and sift project which utilizes Bosch carbon for advanced manufacturing.
My role in the project is to do all the thermal analysis using differential scanning calorimetry, which is DSC, and TGDTA, which is thermogravitometric differential thermal analysis, on these materials.
Paul Rupar, a chemistry professor, and myself had been working with polymer materials for a bulk of our careers, and we met some NASA personnel a few years back, and they let us know about some important research questions that they were tackling and how we might be able to help out with that. And the first aspect of what we're doing is to develop polymers that can support ionic liquids to remove CO2 from the atmosphere of space cabins. For the crew, obviously for health and safety concerns, CO2 has to be removed. We don't want to be breathing too much CO2, or it causes problems. And so the first thing we're doing is developing, like I said, polymers, things that look like this, that we're able to process, and specifically we want to 3D print these materials. We're going to combine them with ionic liquids, which are solvents that have no volatility, so they're very safe to use, especially in space where things might evaporate. This is a very safe solvent that can react with CO2. And when we combine those, they're going to grab the CO2 from the cabin atmosphere and make the conditions hospitable towards the crew in long-term missions. NASA is currently working on different oxygen recovery technologies for long-duration missions. One technology is the Bosch process. This process takes metabolic carbon dioxide and hydrogen to produce water and solid carbon. And in that Bosch reactor, a chemical reaction happens where CO2 is combined with the hydrogen to make water, which is obviously a need for the space crew. We need drinking water, we need water for all sorts of things to live. And it makes that water that we can recover and use, and as well as makes something called Bosch carbon. What do we do with the excess carbon, or does it create a problem? And in some respects, one might view it as a waste product. But I think in a resource-constrained environment, such as in a cabin for space travel, that carbon can actually become an asset. And one of the really clever things that the people at NASA had thought up was to use that Bosch carbon to include it in polymers for 3D printing. Right, so now I don't have to bring up as much material with me into space, and then if I can use the Bosch carbon in 3D printing, I can make what I need when I need it, and I can use that carbon to kind of extend the amount of resources that I have by blending it with the polymer. So in this case, what we're working on is we're taking silicone resins, and this is silicone without the carbon, it's just a transparent rubbery material, and we take that Bosch carbon here and we blend it with the silicone, and the silicone is then cured. And really cool, what we wind up with are parts that are composed of silicone and Bosch carbon. So this is just an example of the carbon infused in that silicone matrix, and we get these black materials, and we can use 3D printing to cast molds or to create molds, and we can fill them with the Bosch carbon and the silicone, and we can make things any shape, size that we want. So again, NASA crew will be able to make things as they need them from things like silicone or other resins, and use that Bosch carbon, which is produced essentially from our breathing. But oftentimes the best research leads to more questions. And so one thing we like to do is to work on refining the Bosch carbon in terms of its particle size and uniformity so that we get even better performance out of the materials that we're producing.